We went to the moon, we landed human beings on the surface of another world, brought them home safe, and we did it 6 times. So going to Mars, that's just the next step, right? Same basic idea, just a little farther away, a little more fuel, a little longer trip, a little more food and water, but fundamentally the same problem. I mean, we did the hard part already. We cracked the nut. Mars is just further down the same road. That's completely wrong. And I'm going to show you exactly why. See, this is one of those situations where common sense leads you straight off a cliff, because the moon and Mars are not the same problem at different scales. They are fundamentally different problems, and the difference is not the kind of thing you fix by building a slightly bigger rocket or by packing a few more sandwiches. The difference is mathematical. It lives inside an equation, a very simple-looking equation, and that equation is merciless. Let me take you through it, and by the time we're done, you are going to understand something that took engineers decades to fully reckon with. Getting to Mars is hard. Landing on Mars is really hard. But getting off Mars and coming home, that is a different kind of hard. That is the kind of hard where nature says no, and you have to figure out whether it really means it. First, let's make sure we agree on what a rocket actually does, because if you don't understand this, none of the rest makes any sense. A rocket works by throwing stuff out the back. That's it. That is the whole secret. You throw mass in one direction, and by Newton's third law, the rocket goes in the other direction. Every rocket that has ever flown works on this one idea. You burn fuel, you heat it up, you blast it out a nozzle at tremendous speed, and the rocket moves the other way. Simple. But there is a catch, and it is a devastating catch. The fuel you are going to burn later, you have to carry it now. And carrying it now means your rocket is heavier now, which means you need more fuel to accelerate all that fuel, which means the rocket is heavier still, which means you need even more fuel to carry that fuel too. You see where this goes? It's a spiral, a vicious, unforgiving spiral. There's an equation that captures this spiral perfectly. It was first worked out by a Russian school teacher named Konstantin Tsiolkovsky back in 1903. The same year, the Wright brothers flew at Kitty Hawk. And here it is in plain words. The change in velocity you can achieve, your delta V, equals the exhaust velocity of your engine times the natural logarithm of the ratio of your full mass to your empty mass. That's it. Delta V equals exhaust velocity times the log of the mass ratio. Now, if you've never tangled with logarithms and exponentials, let me explain what this means in practical terms. Because this is where people get tripped up. They think, well, if I need twice the speed, I need twice the fuel. Wrong. You need much, much more than twice the fuel. The relationship is exponential. If you flip the equation around and ask, how much fuel do I need for a given speed? The answer involves an exponential function, and exponential functions are not kind. Let me give you a feel for it. Suppose your engine throws exhaust out at 3 kilometers per second. That's a decent chemical rocket. If you need a delta V of 3 kilometers per second, you need a mass ratio of about 2.7, meaning your rocket at launch has to weigh about 2.7 times what it weighs when the fuel is gone. Okay, that's a lot of fuel, but it's manageable. Now suppose you need 6 kilometers per second. You might think, well, twice the speed, maybe 5 times the fuel? No. The mass ratio jumps to about 7.4. How about 9 kilometers per second? 3 times the original? The mass ratio is about 20. Your rocket is now 95% fuel by mass, and at 12 kilometers per second, the mass ratio is about 55. At that point, you are basically trying to fly a thin metal can wrapped around a lake of kerosene. There is almost no room left for the actual payload, the stuff you're trying to deliver. This is what engineers call the tyranny of the rocket equation. And it is not an exaggeration to call it tyranny. It dominates everything about space travel. Every rocket that has ever been built has been shaped, twisted, and constrained by this one equation. Let me give you an analogy so you can really feel this in your bones. Imagine you're going on a road trip across a desert, but there are no gas stations anywhere along the route. You have to carry all your gasoline with you. Fine, but gasoline is heavy. And carrying that extra weight means your engine works harder, which burns more gasoline. So you need extra gasoline to haul the extra gasoline. And that extra gasoline is also heavy, so you need more gasoline on top of that. Each new gallon you add gives you a bit more range, but it also makes the car heavier, which eats into the range you just gained. Eventually you reach a point where adding another gallon barely helps at all, because the fuel is mostly being used to carry itself. That's the dilemma rockets face. And it's actually worse than my desert analogy, because a car on the ground just fights friction and gravity going uphill. A rocket has to throw mass overboard at tremendous speed just to accelerate forward. Every second it flies, it's getting lighter, which is good. But it started absurdly heavy, which is the whole problem. The Saturn V, that magnificent machine that took us to the moon, was about 85% fuel by mass at launch. Think about what that means. It weighed about 6.5 million pounds sitting on the pad. 6.5 million. And the part that actually went to the moon and came home, the tiny command module with 3 men inside, weighed less than 1% of the total. All the rest was fuel and the tanks and engines to burn that fuel, and those were thrown away along the route, stage by stage, to shed dead weight. The entire design philosophy of the Saturn V was about getting rid of mass as fast as possible. Use it, dump it, move on lighter. That is not elegance, that is desperation, dressed up as engineering brilliance. The equation forced that design, not the engineer's preferences, the equation. Now let's talk about the moon trip, and let's see why it worked. The delta V to get from the surface of the Earth into low Earth orbit is about 9.5 kilometers per second. That's the hardest part of any space mission, getting off the ground. You're fighting gravity the whole way, you're punching through the atmosphere, and you need tremendous speed, about 9.5 kilometers per second of it. From low Earth orbit to the moon and back, the additional delta V is roughly another 6 kilometers per second, total round trip. And there are some clever tricks. The lunar module was very light. It only had to work in the moon's weak gravity, 1/6 of Earth's. The moon has no atmosphere, so no heat shields needed for landing. And the moon's escape velocity is only about 2.4 kilometers per second. So getting off the surface didn't take that much fuel. They left the bottom half of the lunar module behind. They ascended in just the top part, this little cabin, barely enough for 2 men. They rendezvoused with the command module in orbit, transferred the crew, and threw the ascent stage away too. Every kilogram mattered. Every decision was about saving mass. And it worked. Barely in some cases, but it worked. The total delta V budget for the whole Apollo mission, from Earth's surface to the moon's surface and back, was roughly 15 to 16 kilometers per second. That's a monstrous number. The Saturn V was the most powerful rocket ever flown, and it could just barely do it. So now, Mars. The first thing you have to understand is how far away Mars actually is. Not in some abstract sense, in a practical mission planning sense. The moon is about 3 days away. You light your engine, coast for 3 days, and you're there. If something goes wrong, you can turn around. Apollo 13 proved that. They swung around the moon and came home in a few days, battered but alive. Mars is not 3 days away. Mars, at its closest, is about 55 million kilometers from Earth. At its farthest, about 400 million kilometers. And you can't just point your rocket at Mars and go, because Mars is moving. Earth is moving. Everything is orbiting the sun at different speeds and different distances. You have to launch at just the right time, follow a curved path called a Hohmann transfer orbit, and arrive at Mars about 8 or 9 months later. 8 or 9 months, in a spacecraft, in deep space, with no possibility of turning around because you're already committed to the trajectory. Let me make sure that sinks in. 8 or 9 months. On the space station, if something goes terribly wrong, you can pile into a Soyuz capsule and be on the ground in a few hours. On the way to Mars, if something goes wrong, you are in a metal tube, hurtling through the void at tens of thousands of kilometers per hour, and your options are to fix it yourself or die. There is no abort. There is no safe harbor between here and there. The vast majority of the journey is spent in a region of space where the sun's radiation is unfiltered. Micrometeorites are an ever-present threat, and the nearest human being not on your spacecraft is getting farther away every day. And people talk casually about this trip as though it's a long airplane flight, as though boredom is the main concern. It's not. The main concern is that you're living inside a complex machine for the better part of a year, and if any critical system fails, engine, life support, navigation, power, there is no emergency landing strip between Earth and Mars. Nothing. Just vacuum. But let's set aside the travel time for now. Let's talk about delta V, because that's what the rocket equation cares about. From low Earth orbit, the delta V, to get on a transfer orbit to Mars is about 3.6 kilometers per second. Then you need to slow down when you arrive, maybe another 1 to 2 kilometers per second to get into Mars orbit. Then you need to descend to the surface. And this is where Mars starts to show its teeth. Mars has an atmosphere. You might think that's good news. On Earth, we use the atmosphere to slow down. Parachutes, heat shields, air resistance, wonderful stuff. Saves you all the fuel you'd need for a powered landing. And the moon has no atmosphere at all, so everything there had to be done with rockets. But Mars has a terrible atmosphere. Not terrible in the sense that it's unpleasant, although it is. Terrible in the engineering sense. It's the worst of both worlds. The atmosphere of Mars is about 1% the density of Earth's atmosphere at sea level. 1%. Standing on the surface of Mars is like standing at an altitude of about 35 kilometers above the Earth, about 3.5 times higher than commercial airplanes fly. Up where there's essentially nothing. That's how thin the air is on Mars, at ground level. So what does that mean? It means the atmosphere is thick enough that you cannot ignore it. When a spacecraft comes screaming in at 5 or 6 kilometers per second, even that wisp of air generates enormous heating. You need a heat shield. You have to manage the thermal loads. It's a real atmospheric entry with real danger, but the atmosphere is far too thin to stop you. On Earth, a parachute can slow you from supersonic speeds to a gentle landing. On Mars, a parachute helps, but it can only slow you to about 200 miles per hour, maybe a little more, maybe a little less, depending on the size of your parachute and the weight of your vehicle. And 200 miles per hour is not a landing speed, that's a crashing speed. So after your heat shield has slowed you from hypersonic to supersonic, and your parachute has slowed you from supersonic to something still terrifyingly fast, you then have to fire rockets to do the final braking. For a small robotic lander, this is manageable. The Viking landers that touched down on Mars used a combination of heat shields, parachutes, and retro rockets, and they weighed under a metric ton. It worked. The engineering was beautiful. But those were small machines with no passengers. And the signal delay from Mars to Earth is over 10 minutes, sometimes over 20. That means no one on Earth can steer the landing in real time. The machine has to land itself, and every step of the sequence has to work autonomously. Any failure, and you've just made a very expensive crater. A human mission to Mars needs to land something like 20 to 40 metric tons on the surface. People, habitats, life support, food, equipment, power systems, and possibly the fuel and vehicle for the return trip. Here's where the nightmare truly begins. That parachute trick does not scale. You cannot just build a bigger parachute for a heavier payload and expect it to work. The physics doesn't cooperate. The atmosphere is so thin that the parachute would have to be absurdly large, hundreds of meters across, and deploying something like that at supersonic speeds in Martian atmosphere is, to put it gently, beyond what we currently know how to do. So for heavy payloads, you need to use rockets for most of the deceleration. And every kilogram of rocket fuel you bring for landing is a kilogram you had to carry from Earth. The tyranny of the rocket equation again. NASA has estimated that for an all-propulsive landing on Mars, every 1 metric ton you want on the surface requires about 20 metric tons in low Earth orbit. That ratio, 20 to 1, should give you nightmares if you're planning a Mars mission. But I keep getting ahead of myself. All of it, is just the problem of getting to Mars. Let's suppose, by some magnificent effort, we solve it. Let's suppose we land a crew on Mars with their habitat and their supplies and their equipment. Let's suppose everything goes perfectly. Now they want to come home. And this is where the universe laughs at you, because getting off Mars is, in many ways, harder than getting to Mars. Not because Mars has stronger gravity than Earth, it doesn't. Mars has about 38% of Earth's surface gravity. The escape velocity from Mars is about 5 kilometers per second compared to 11.2 for Earth. So in raw gravitational terms, Mars is easier to leave than Earth. But you're not on Earth anymore, you are on Mars. And Mars has no Kennedy Space Center, no vehicle assembly building, no army of engineers, no factory down the road manufacturing rocket parts, no tanker trucks delivering fuel. You are on a barren, frozen, airless world, 55 million kilometers from the nearest machine shop, and you need to build or bring everything required to launch a rocket from the surface of another planet. Think about what it took to launch the Saturn V. Thousands of people, billions of dollars, entire industrial supply chains. Just the liquid oxygen and liquid hydrogen to fuel that rocket required enormous industrial infrastructure. Cryogenic processing plants, pipelines, pumps, storage tanks. All of it had to function flawlessly, or the rocket doesn't fly. On Mars, you have none of that. If you bring your return fuel with you from Earth, you have to carry it all the way to Mars, land it on the surface, keep it stored for the duration of your stay, and then use it to launch. And remember the rocket equation. Every kilogram of fuel you bring for the return trip is a kilogram that had to be launched from Earth, transferred to Mars, and landed safely. The mass multiplier is staggering, that 20-to-1 ratio for landing. It gets worse when you include the fuel for the return trip, because now you're landing fuel that you need to launch. Let me try to sketch the numbers roughly. To get a crew off the surface of Mars and into low Mars orbit, you need a delta V of about 4.1 kilometers per second. That includes gravity losses and a little margin. From low Mars orbit, you need to get on a transfer orbit back to Earth, which costs another 2.3 kilometers per second. So just getting off Mars and heading home costs about 6 to 7 kilometers per second of delta V. With a good engine, say a specific impulse of 450 seconds, that means your rocket at launch from Mars needs to be roughly 80% fuel by mass. 80% fuel on a planet where there is no fuel. And it's actually worse than that, because the mass I just calculated doesn't include the heat shield you need for Earth re-entry, or the life support for the months-long journey home, or the food and water, or the structural mass of the vehicle, or any margin for error. Include all of that, and the mass of fuel compared to everything else becomes obscene. Here's another way to see it. Remember, we got to the moon and back with a delta V budget of about 15 to 16 kilometers per second. The total delta V for a round trip to Mars, including launch from Earth, transit to Mars, landing, launch from Mars, transit back, and Earth re-entry, is in the neighborhood of 18 to 22 kilometers per second, depending on the trajectory and the mission architecture. That might not sound like much more than the moon mission, only a few extra kilometers per second. But the rocket equation doesn't care about your intuition. A few extra kilometers per second, when you're already at the edge of what's possible, means an exponential increase in the fuel required. You're not adding fuel, you're multiplying it. Going from 15 to 20 kilometers per second of delta V can mean tripling or quadrupling the initial mass of the rocket. For the moon mission, the Saturn V weighed about 3,000 metric tons. A Mars mission with the same propulsion technology, bringing all the return fuel, might require a spacecraft assembled in orbit weighing tens of thousands of metric tons. Nobody has ever built anything remotely close to that in space. But wait, I haven't even mentioned the cruelest constraint yet, orbital mechanics. The planets don't wait for you. Earth and Mars orbit the Sun at different speeds, at different distances. Earth goes around in 365 days. Mars takes about 687 days. They line up in a favorable position for transfer roughly every 26 months, 2 years and 2 months. That is the synodic period. You can only launch efficiently when the planets are in the right positions. This means if you land on Mars and you want to come home, you cannot just leave whenever you feel like it. You have to wait for the next launch window. And depending on your mission architecture, that means sitting on Mars for anywhere from about 30 days to 500 days, waiting for Earth and Mars to dance back into the right alignment. The most energy-efficient mission profile is called a conjunction class mission. You fly to Mars in about 9 months, you stay on the surface for roughly 500 days, and then you fly home in another 9 months. The whole trip takes about 2.5 to 3 years. The long stay on Mars is not a choice, it's a consequence of orbital mechanics. If you try to shorten the stay, you pay an enormous delta V penalty, because you're fighting the natural rhythm of the orbits. A short stay mission of 30 to 90 days on the surface requires a much more energetic return trajectory, sometimes spending over a year in transit just to get home, and the total delta V goes through the roof. So your crew is on Mars for a year and a half, no matter what. During that time, they are exposed to cosmic radiation with no protective magnetosphere, no thick atmosphere, just a thin veil of carbon dioxide. On Earth, we are shielded by a magnetic field that deflects most charged particles from the Sun and from deep space. On Mars, that shield does not exist. The atmosphere provides a little protection, but remember, it's 1% the density of Earth's. That means cosmic rays, high-energy particles traveling at nearly the speed of light, are hitting the surface of Mars all the time, and they're hitting your crew. This isn't sunburn. These are particles that can shred DNA. They pass through the walls of your habitat, through the hull of your spacecraft, through your body. They break chemical bonds in your cells. The damage accumulates. On the space station in low Earth orbit, astronauts are still partially shielded by Earth's magnetosphere. Even so, they receive radiation doses many times higher than what we consider safe for workers in nuclear power plants. On Mars, the doses are worse. Over the course of a 3-year mission, the cumulative radiation exposure is estimated to be roughly 1 sievert, which significantly increases the lifetime risk of cancer. And there is no way to fully shield against galactic cosmic rays without meters of solid material around your habitat, which is mass you cannot afford to bring. They are living in a habitat that must be self-sufficient, because the nearest resupply is about 9 months away by rocket, and you can't even send a resupply unless the launch window is open. If something breaks during the wrong part of the orbital cycle, there is nothing anyone on Earth can do about it for months, possibly over a year. If a crew member gets seriously ill or injured, there's no hospital. There's no helicopter evacuation. There's the crew's own medical training, whatever supplies they brought, and hope. And psychologically, 4 to 6 people in a habitat the size of a couple of shipping containers, isolated from every other human being in the universe by millions of kilometers, and a communication delay measured in minutes, for a year and a half, with the knowledge that if something goes catastrophically wrong, no one is coming to help. Antarctic winter-over crews, submariners, space station astronauts, they've all taught us something about isolation. It degrades performance, it strains relationships, it affects judgment. And those missions last months, not years, and those people all know that rescue is at least theoretically possible. On Mars, it is not. Now let's come back to the fuel problem, because I want you to really feel the weight of it. Suppose you are designing a Mars return vehicle. It needs to carry, let's say, 4 crew members, with life support for the journey home, maybe 200 days, with a heat shield for Earth re-entry, with the structural mass of the vehicle. Let's say the dry mass, everything except fuel, is around 10 metric tons. That's actually very optimistic. It's probably more, but let's be generous. To get a delta V of about 6.5 kilometers per second, with a specific impulse of 450 seconds, the exhaust velocity is about 4.4 kilometers per second. The mass ratio you need is e to the power of 6.5 divided by 4.4, which is e to the power of about 1.5, which is about 4.5. So your fully fueled vehicle needs to weigh about 45 metric tons for 10 metric tons of payload. That's 35 metric tons of fuel. 35 metric tons of rocket fuel. On Mars, where there is no fuel, where the nearest gas station is 55 million kilometers away, and every one of those 35 metric tons of fuel had to be launched from Earth. It had to survive the 9-month cruise to Mars. It had to be landed on the surface, through that miserable atmosphere, without crashing. It had to be stored for a year and a half without boiling off or degrading, and then it had to work perfectly when you light the engine. If you bring all this fuel from Earth, the cascade of mass through the rocket equation is catastrophic. You need fuel to carry the fuel. You need fuel to land the fuel. You need fuel to launch the fuel from Earth. Each step multiplies the mass. By the time you trace it all back to the launch pad on Earth, the total mass required is enormous, not just expensive, not just impractical, bordering on impossible with current technology. This is why some very smart people have proposed a different approach. Instead of bringing all the fuel from Earth, why not make it on Mars? This concept is called in situ resource utilization, or ISRU. The idea is that you send a chemical processing plant to Mars ahead of the crew, and it uses resources on Mars itself to manufacture rocket fuel. Mars's atmosphere is about 95% carbon dioxide. If you can crack that carbon dioxide, split it into carbon and oxygen, you've got your oxidizer right there. If you can find water ice, and we believe there is water ice just beneath the surface in many locations, you can split the water into hydrogen and oxygen, combine the hydrogen with the carbon, and you can make methane. Methane and oxygen, that's a rocket propellant combination that actually works quite well. That's what certain engines are designed to burn. On paper, this is brilliant. You make your fuel on Mars, and you eliminate the need to carry it from Earth. The savings in mass are extraordinary. Instead of launching 35 metric tons of fuel from Earth and somehow getting it all to the Martian surface, you ship a processing plant that weighs maybe 1 or 2 metric tons, and you let it run for a year or so, slowly filling your tanks with locally produced fuel. The rocket equation becomes much more forgiving because you've broken the chain. The fuel doesn't have to trace back to Earth anymore. But, and there is always a but in engineering, making fuel on Mars is something we have never done. Not once, not even a small demonstration, at meaningful scale. We've sent robots to Mars, clever little machines that have done remarkable science. but none of them has ever chemically processed Martian atmosphere or Martian ice into usable rocket fuel at any useful volume. The chemistry itself is well understood. You take carbon dioxide from the Martian atmosphere, you apply energy, and you can split it into carbon monoxide and oxygen. Or you find water ice beneath the surface, electrolyze it into hydrogen and oxygen, and combine the hydrogen with carbon to produce methane. Methane and oxygen burn nicely in a rocket engine. But knowing the chemistry and doing the chemistry on another planet are two very different things. Going from a laboratory demonstration to 35 metric tons of fuel on Mars requires scaling up by a factor of millions. That's not an incremental improvement. That's a different machine entirely. And it requires reliability on Mars in an environment that is actively hostile to machinery. Martian dust is not like Earth dust. It's fine, electrostatically charged and chemically reactive. It contains perchlorates, which are toxic and corrosive. This dust gets into everything. It settles on solar panels and reduces their output. It works its way into seals and bearings. It coats optical instruments. Robotic landers on Mars have suffered greatly from dust accumulation. Solar-powered machines gradually lose power as their panels get coated. And if they can't clear the dust, they eventually go dark. Now imagine your fuel plant has to run continuously for 12 to 18 months. Processing Martian atmosphere day and night, compressing gases, running chemical reactions at high temperatures, storing cryogenic liquids, all while Martian dust does its best to infiltrate every component. And temperatures swing from about minus 20 degrees Celsius during the day to minus 70 or 80 at night. That thermal cycling alone stresses materials, opens microscopic cracks, and degrades seals over time. And here's what worries me. If the fuel production fails, your crew is stranded. There is no backup. There is no second chance. If the ISRU plant breaks down 6 months into its operation and only fills half the tanks, what then? You cannot phone home and have someone send more fuel. Even if you had a rocket ready on Earth with fuel to send, it takes 9 months to get there, and that's only if the launch window is open. So you start to see the shape of the problem. It's not just one challenge. It's a web of challenges, all tangled together, and each one depends on the others. You need the fuel production to work, which means you need the machinery to work, which means you need the power systems to work, because cracking carbon dioxide takes energy, lots of energy. Solar panels on Mars produce maybe half the power they'd produce on Earth, because Mars is farther from the sun. Dust settles on the panels and degrades their output. You could bring a nuclear reactor, but that's another piece of equipment you have to land safely and set up on an alien world. Let me step back and tell you what I think is the deepest reason this problem is so hard. And it's not any single engineering challenge. It's the compounding of uncertainties. For the moon missions, everything was close. If something went wrong, you were days from Earth. Radio signals traveled in about 1.25 seconds. Mission control could talk you through a problem in real time. The whole trip lasted about 8 days. 8 days of consumables. 8 days of keeping the machinery running. The risk window was narrow. For Mars, the risk window is years. 2.5 to 3 years. The radio delay is anywhere from 3 minutes to 22 minutes, depending on where the planets are. If you're waiting for Mars to answer a question, the round trip for your signal could be 44 minutes. Mission control cannot talk you through a crisis in real time. You are on your own. And every system on that spacecraft, every life support unit, every engine component, every seal, every valve, has to work, or work well enough, for 3 years straight, with no resupply, no spare parts depot, and no rescue mission possible. Think about your car for a moment. How often does something go wrong? A flat tire, a blown fuse, a strange noise from the engine. Maybe once a year, something needs attention. Now imagine your car had to work perfectly, without maintenance from anyone outside, for 3 years, in conditions far worse than any road on Earth, in temperatures that drop to minus 60 degrees Celsius at night, in an atmosphere that's practically a vacuum, with fine abrasive dust that infiltrates every seal, every bearing, every joint. The engineers who work on this problem are not naive. They know all of this, and that's why no one has done it yet. Not because they lack ambition, not because they lack funding, though funding is always short, but because the physics is genuinely, deeply, fundamentally more difficult than anything we have ever attempted. And let me remind you, just getting robotic spacecraft to Mars has proven murderously difficult. Of all the missions ever launched toward Mars, roughly half have failed. Half. Crashed. lost contact, missed the planet entirely, burned up, landed too hard, deployed a parachute that didn't open, fired an engine that didn't light. The Soviet Union sent mission after mission in the 1960s and 70s, and most of them failed in one way or another. Mars has a reputation among mission planners. Some of them joke, darkly, about the galactic ghoul that eats Mars spacecraft. It's not a ghoul, it's the accumulated difficulty of doing precision engineering across millions of kilometers with no room for error. And that's for robots. Robots that don't need food, water, oxygen, or a ride home. Let me make one more point that often gets overlooked. Gravity, not Mars gravity, Earth gravity, the gravity waiting for you at the end. When your crew comes home from Mars after 2.5 to 3 years in space, most of that time spent in either low gravity or zero gravity, their bodies will be in rough shape. Bones lose density in low gravity, about 1 to 2% per month in microgravity, even with exercise. Over the course of a Mars mission, astronauts could lose 10 to 20% of their bone density in load-bearing bones. Hips, spine, legs, that bone doesn't fully come back, even after years on Earth. Muscles atrophy, despite hours of daily exercise. The heart, which is a muscle, shrinks and weakens because it doesn't have to pump as hard in low gravity. The cardiovascular system deconditions. Fluids that normally pool in your legs redistribute toward your head, causing pressure changes in the eyes that can damage vision. Some astronauts have come back from the space station with permanent changes to their eyesight. The inner ear, which governs balance, goes haywire after months in microgravity. Your brain adapts to floating. When you suddenly have to stand upright in a gravity field again, the system crashes. After a year on the space station, astronauts can barely stand when they return to Earth. Some have to be carried out of their capsule on stretchers. They undergo months of rehabilitation to walk normally again. Now imagine you've spent 9 months in zero gravity going to Mars. You've spent 500 days in 38% gravity on Mars, which is better than zero but much less than Earth. And then you've spent another 9 months in zero gravity coming home. When you hit Earth's atmosphere, you are pulling several Gs during re-entry. 3 Gs, maybe 4. Your weakened heart has to handle forces it hasn't experienced in nearly 3 years. Your brittle bones have to absorb the shock of landing. This is not a trivial concern, it's a genuine threat to survival, and we do not yet have good countermeasures, despite decades of research on the space station. So let me put it all together. To return from Mars, you need to solve simultaneously all of the following. You need enough fuel to launch from the surface and get on a trajectory home, either brought from Earth at enormous cost or manufactured on Mars with technology that doesn't exist yet. You need a launch vehicle that has survived the trip to Mars, the landing on Mars, and a 1.5 years sitting on the Martian surface. You need a heat shield that works after years in space. You need life support that functions for months on the return journey. You need to launch at exactly the right time, within a narrow window dictated by orbital mechanics. You need the crew to be healthy enough to survive re-entry into Earth's atmosphere after years of physical deconditioning. And you need all of this to work with no possibility of rescue and no margin for major failure. Any one of these problems is a serious engineering challenge. Taken together, they represent a wall of difficulty that we have not yet found a way to climb. Now, am I saying it's truly impossible? No. I chose my words carefully. I didn't say it's impossible. I said the common belief that it's straightforward, that it's just the next step after the moon, is wrong. The physics doesn't forbid it. The laws of nature don't say you can't return from Mars. They say the price is enormous, and the price has to be paid in full, in mass, in energy, in reliability, in time, and in risk. Nature doesn't negotiate. It doesn't care how badly you want to go. It doesn't care how inspiring the speeches are or how big the budget is. The rocket equation is not moved by enthusiasm. It asks how much mass you have, how fast your exhaust goes, and how much velocity change you need. And if the numbers don't work, the rocket doesn't fly. There's a saying among rocket engineers. They say the rocket equation is not a wall, it's a filter. It doesn't prevent you from doing things. It filters out everything except the solutions that are genuinely good enough. Borderline solutions, almost good enough solutions, the ones where you hope and pray that everything goes right, those get filtered out. The equation demands engineering with deep margins, or the mission fails. And for a Mars return mission, we do not yet have those margins. We are, right now, at the stage where the numbers almost work if everything goes perfectly, and several technologies that have never been tested at scale, perform exactly as hoped. Almost. That is not good enough to put human lives on the line. Let me suggest how this might eventually be solved, because I don't want to leave you in despair. That's not how physics works. Physics tells you the constraints. It tells you what's hard. It's your job to find the way through. The most promising path involves several ideas working together. First, in situ fuel production. If you can make your fuel on Mars reliably at scale, the mass problem shrinks dramatically. But this needs to be demonstrated, tested, proven, long before you send a crew. Second, pre-positioning. You don't send everything at once. You send cargo missions ahead, 2 years before the crew. Fuel production starts. Supplies are landed and checked. The return vehicle is on the surface, fueled and ready, before a single human being leaves Earth. If anything fails, you don't send the crew. You wait for the next window and try again. This approach buys you time and redundancy. Third, orbital staging. Instead of launching everything from the surface of Mars directly to Earth, you assemble pieces in Mars orbit. Maybe the return vehicle stays in orbit, and only a small ascent vehicle launches from the surface. The ascent vehicle docks with the return ship, the crew transfers, and the bigger ship carries them home. This is how Apollo worked, and it's how Mars missions will probably work too. It saves the mass of bringing the entire return vehicle down to the surface and back up again. Fourth, and this is the long game, new propulsion. Chemical rockets have a fundamental limit on exhaust velocity, and therefore a fundamental limit on how much delta V you can squeeze out of a given mass of fuel. The best chemical engines top out at an exhaust velocity of around 4.5 kilometers per second. That's set by the chemistry. You can't burn hydrogen and oxygen any harder than thermodynamics allows. You're up against a wall. Nuclear thermal rockets offer a way past that wall. Instead of burning fuel chemically, you heat hydrogen gas by passing it through a nuclear reactor. The reactor can achieve temperatures that chemistry cannot, and the exhaust velocity roughly doubles to about 8 or 9 kilometers per second. That doesn't sound like much, just doubling. But remember, the rocket equation is exponential. Doubling the exhaust velocity doesn't just cut the fuel in half. It transforms the mass ratio. A mission that requires a mass ratio of 20 with chemical rockets might only need a mass ratio of 4 or 5 with nuclear thermal. The difference between barely possible and actually feasible. These rockets were studied extensively in the 1960s under a program called NERVA. They built them, they tested them, they worked. And then the program was canceled because the political will evaporated and the funding went elsewhere. That was over 50 years ago. We still don't have a flight-rated nuclear thermal engine. It remains one of the great missed opportunities in the history of space exploration. Nuclear electric propulsion is another option. Instead of heating gas directly, you use a reactor to generate electricity, then use that electricity to accelerate ions to extremely high velocities. The exhaust velocity can be 10, 20, even 50 times higher than chemical rockets. The fuel efficiency is extraordinary, but the thrust is tiny, mere fractions of a Newton. You can't use it to launch from a planet. You can't use it for quick maneuvers. It's like the difference between a sprinter and a marathon runner. Chemical rockets sprint. Ion engines run marathons slowly, over months, gradually building up speed. Useful for cargo, perhaps, not for getting a crew home in a hurry. Each of these ideas helps. Together they might be enough, but together they also represent an engineering program of staggering complexity and cost. Decades of development, hundreds of billions of dollars. And at the end of it, the mission is still dangerous. Not Apollo dangerous, where you're gone for 8 days and the risks are concentrated in a few critical hours. Mars dangerous, where you're gone for 1,000 days and the risk never lets up. I want to leave you with one image. You're standing on Mars. The sky is a pale butterscotch pink. The ground is rust red, scattered with rocks. It is quiet. The kind of quiet you have never experienced, because there is almost no atmosphere to carry sound. The sun is smaller than you're used to. Earth, when it's visible, is just a bright dot in the sky, a blue spark. And everything you need to get back to that blue spark, every atom of fuel, every bolt, every line of code in the guidance computer is either in the rocket behind you or doesn't exist yet. That rocket behind you, it has to work. It cannot almost work. It cannot mostly work. It has to work completely, perfectly, the first time, because there is no second launch, no tow truck, no emergency landing strip. And the physics that governs whether that rocket has enough energy to carry you home is captured in an equation written by a schoolteacher in Russia over a century ago. An equation that says the fuel you need grows not in proportion to the difficulty of the mission, but exponentially. We will go to Mars someday, I believe that, but we will go when we have earned the right to go. When the numbers truly work. When the fuel is ready, the vehicles are tested, and the margins are real. Not when someone gives a speech about destiny. Nature has no interest in destiny. It has laws. And the laws say that getting off Mars and coming home is one of the hardest things human beings will ever attempt. Think about that equation tonight. Think about what it means that fuel requirements grow exponentially. Think about what it means that an atmosphere can be too thin to save you but thick enough to burn you. Think about what it means to be sitting on a planet where the nearest help is months away, even at the speed of light. And then think about this. Somebody will solve it. Somebody always does. That's the other thing about physics. It tells you how hard the problem is. It never tells you to give up.